robot that walks. Fortunately, we have a real expert about that. Roboticist, PhD, does this stuff for a living, made some amazing looking walkers. He's here to tell us all about them. This is Dr. Chris Parrott.
Hi. Thank you very much for having me and that warm welcome. So yeah, as I titled the talk, I'm going to be talking about the challenges of multi-leg robots, and I want to kind of ask the question to you: will your next Pywell's entry be a walker? So when you think of walking robots, you probably think of all of these. And when you see these, particularly the videos like recent Spot ones, it can kind of give the impression that walking robots are hard to get started with because of all the amazing things they're doing. But today I'd like to show you that that's not the case and that you too can build a walking robot, and it's perhaps not as hard as you think. So first, a bit about me and my background with walkers. I actually started in my teenage years by modding walkers into the video game Total Annihilation, a strategy game with armies battling and stuff. So here's some clips I took from that. And that's kind of what got me hooked. And I ended up going on to the Links Motion forum, which was the place on the internet at the time for walking robots. And through the guides on there, ended up building this one, which for some reason is not playing. Okay. Right, so videos may not be playing. Oh. Anyway, it's here, you can see it. Since then, went on to do a PhD in robotics, not related to anything walking robots, but equally as cool. Just to give you a sense that I did this before getting a formal qualification with robotics. Then I've been exploring walkers in simulation ever since. And more recently, as you may have seen me tweet about, I've been building walkers for inspecting water pipes at work. So why would you want to build a walker then? Well, a few positives. They can move in any direction, much the same way as the cannon wheels. Big thing being they can adapt to rough ground. And also, because you've got these degrees of freedom in the robot legs, you can adjust your body height, position, and angle. So if you wanted to raise your camera up, you don't need a separate mechanism for that. The body can just tilt as you need. Reasons you may not want to, though: lots of moving parts, so points of failure. Complex to control, but hopefully some of the stuff I'll talk about today will show you what's actually involved in that. And yes, they are actually slower than other movement options, as Brian said at the start of today. But the real reason you want to make one is because they're cool. And yes, here's my two. So the big one, which I've got on here, I built about 8 years ago, predates Raspberry Pi, so it's Arduino based. And the smaller one I built about a month ago purely for the purpose of preparing this talk. And so the cost difference is the small one about £20, the other one £2,000. So if you're deciding on a walker, you need to ask yourself, how many legs do you want? Do you want to go biped, quadruped, hexapod, octopod? I personally recommend as a starting point hexapod because it makes things a little bit easier. You can do octopod as well, but it becomes just extra cost for no real benefit there. Also, number of joints per leg. I recommend having 3 minimum for a spider-like robot. And if you're going for a biped, really you want 6, although there are exceptions to this depending on what you actually wanted to do. Also, are you actually wanting it to walk on the rough ground that I mentioned? In that case, you'll need to have some sort of sensing, such as contact sensors in the feet. For driving the joints, you'll pretty much, as you may have guessed, want to use servos. They're ideal because they have a motor with built-in feedback, like was talked about earlier, and they go to a position and stay at it, but with the problems that come with loops for feedback. But there are many out there, as I'm sure you've looked at, and there's certain considerations you may need to think about, particularly cost, because for hexapods you need 18 minimum, so it quickly adds up. Just multiply everything by 20. How big is it going to be? Because that will affect the size of the actual motors you want, but also the torque that you're able to get, which affects the overall weight. All of these things are interconnected, and also speed, because that'll affect the top speed that they're able to walk at. In terms of servo options then, hobby servos you're familiar with, PWM controlled and only do proportional feedback, so it comes with the cons of that, but there are a wide variety available. They don't give any sort of feedback to your microcontroller though, so you basically tell them to go to a position and hope they're there. But recently there have been servos like this Adafruit one which give you an extra pin for that, and you can also hack normal servos with that pin if you want. Now, you would probably want to use a driver for this, and there are many options for up to 16 servos, but as I mentioned, the hexapod needs 18. And there's fewer options for that. So here's an example board that you can get. The Lynx Motion one goes up to 32. As of yet, I've not seen any hats that do 32 servos. So that becomes a problem for doing the higher number of motors per leg. Also, mentioning those analog servos, the analog feedback servos, there are no servo drivers that I've been able to find that have connections for those. So you'd have to DIY your own solution if you wanted to go down that route. Now, on the more advanced side, you've got smart servos. So these are specifically designed for robotics. They have a built-in PID loop, which you can tune, and they're on a communication bus. So that means that you can, it makes wiring easier for starters because you don't need a wire per motor, you just need a wire per leg. And also lets you read back the ankle current, temperature, and other parameters of the motors to make sure they're actually doing what you're doing. But these are quite expensive if you've ever had a look. Right? The Dynamexel ones, maybe £50 at the low end, and go up to several hundred from there. So you may want to look at doing DIY. So with what was talked about earlier, get a motor, encoder, driver, microcontroller, and fashion your own servo. Or you can buy certain off-the-shelf parts, such as the Mechaduino and O-Drive, which combine the latter three things together, so you just need to supply a motor. Now, with that, you've decided I'm going to build a robot, walking robot. Some tips for you. If you're using hobbyist servos, although this can also apply to the other ones, calibrate your servos. By that, I mean, figure out what pulse or command you need to send to it to get the actual minus 90, plus 90, and 0 degrees. I wouldn't recommend just getting minus 90 and plus 90, because that's assuming the range will be linear, which you can't guarantee. I've found having those three values at a minimum in your calibration lookup to be quite useful, and make some sort of jig like that for doing the calibration. If your robot's heavy though, then you may want to actually calibrate the robot or the motors in place on the robot and add some jig or some such to the side. So here's one I 3D printed. I recommend actually calibrating the robot upside down, because then gravity will be acting on the calibration, and that should alleviate some of the steady state offset with the cheaper motors. So at least it's working in the direction you want it to. Go for Metal Gear servos if possible. They'll last a lot longer. They can still break, but it's usually other parts of the motor that break before the gears in that case, as I've found. Or you blow your motors because you forget to wire them up properly. The gears will be fine if you go Metal Gear. Also, if your robot is on the heavy side, then maybe consider adding springs on the legs to reduce the load that they're facing against gravity. Oh, and it may be tempting to have your heaviest parts sort of to the back, like if you've got a particular theme you're going for, but then you put in disproportionate load upon the legs, so really have your batteries or heaviest parts at the middle. Now, going on how to walk, and this is meant to be a video, but I don't know why it's playing, but you can see during the lunchtime I've got my simulator running. There's two separate but connected problems. The first is, how do you move each leg to touch a position in space? Think of it as just touching with your finger. If that is one problem, and then the second problem is, if you've got all your legs doing this touching, how do you move those points that they're following to create walking? So think of it as the output of problem 2 goes into the input of number 1. Also, if you're going for something like a quadruped, you may want to consider, how do you stay balanced? Answering number 1 then, we've got inverse kinematics. This is the process of finding the joint angles of the leg that place its end at the target. And as you may guess, this is solvable with trigonometry. So this is at least the one point in adult life I've found trigonometry to be useful. And yeah, you've got an example here. If you're going for 3 joints, like they recommend for a spider, then there's 2 mathematical solutions, either an over or underarm. If you've got more joints, then there's technically infinite number of solutions, but you can find one by either grouping certain joints together so that they have the same angle, or having some motors point in a particular direction, such as having all the tips point down. Then you're basically reducing the problem back to 3 joints, and then you can solve that. So with that solving problem 1, you then need to define how do you actually want the robot to walk, and this is what's known as a gait. And this can be defined as a repeating cycle of steps that are taken by a set of legs to achieve motion in a direction. And we've got 2 examples here. You can think of it as each leg is in either 2 states, either a striding state where the leg is off the ground or high, and a stance state where it's on the ground or low. And yeah, biped, each leg alternates, and quadruped, only one leg moves at a time, although you can do any pattern of these that you want. And this, I should say, is a cycling thing, so it goes 0 to 1 and then back to 0 in a circle, effectively. From this, you will then need to go do gait generation of actually create the walking, which is where we convert that definition into a set of offsets that we want to apply to the points that the legs are touching. And for that, you want to separate one of the entries out into a height and a distance offset. The height offset starts at 0 and, as you may guess, ends at 0, going up to a peak height, which can be whatever value you want, during the middle. And you can do any sort of shape there. I go for an upside-down parabola because it becomes quite useful for doing rough ground walking. The distance at the start of the stride is all the way backwards, and then as the stride moves forward, goes to the front. Then during the stance, goes to the back. When you combine these together with the inverse kinematics, you end up with that happening. I'll just let it play for a moment. And you can imagine if you apply this to all 4 legs of a quadruped, for example, and put it on the ground, this will walk. Now, a brief mention of balancing. There are 2 ways to do it, and I think these videos won't play, so you'll have to look at it afterwards. In this video, the robot's lifting 2 legs at a time, and it's balancing with an IMU, so very similar to the balance bots and like face plant, where it's making continual corrections to avoid falling over. Problem with this is that if your program locks up for any reason, the robot will obviously fall over. The alternative for that, and this is what I've got demoed out in the robot area, is the static stability, or static balancing, where you move the robot center to be over the legs that are going to be on the ground at the next stride, and before you lift the leg, so that at any point, if it locks up, it will just effectively pause. Yeah, and so to wrap up then, and kind of attempt to answer the title of the talk, if you're looking for a new challenge, then I highly recommend it. Not only will you learn a lot of new things about robotics, but you get a cool new robot at the end. Whether it's good for the challenges of Pi Wars is up to the community to figure out the best way to optimize walkers. But maybe in the future years, there'll be challenges that take more advantage of their capabilities. So this may be a bit intimidating to get started, though, so I have actually put my walking simulator, and again, this should be a video playing, I put that on GitHub, and you'll be able to see it outside as well. Also, I'm planning to work on a custom hat that drives 32 servos and will do everything on board, the walking calculations and everything. So much like the Pixie Cam, it's just something you'll put on and it'll be able to do the walking. So with that, thank you very much for listening.
We have one question.
Okay. I guess.
What's the advantage of using a walker and making pipes as that? Normally I see robots using wheels all the time. In just a normal pipe, not really. When you've got a pipe network with lots of interconnections, the surface becomes not just a cylinder, and there may be obstacles, to put it politely, that you may need to navigate around. Also, we're looking at having the legs themselves be sensors that we can send vibrations into the ground. So we always have those contact points because we're doing the walking.
Okay.
All right, thank you, Chris. We look
Yeah.
forward to having a look at your robots in the
Yeah.
past. Thank you.